Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Nuclear Force and its Properties Part 6 from paper Nuclear and Particle Physics. After studying this module, you should be able to understand the following things. Number one, the terms contributing to the nuclear interaction. Number two, the symmetry properties of nuclear interaction. And number three, the importance of nuclear interaction in general. Nuclear force. In this particular slide, we are going to study the basic properties of nuclear force. That what is nuclear force and what are its properties. So nuclear interaction has the following properties. Number one, it's finite range. What does that mean? That it can be experienced by the nucleons only within certain limited domain. And what is that domain? That domain is basically the size of nucleus. Only within the nuclear volume, the nucleons feel the nuclear force. So this is one of the very important property of nuclear force, that it's finite range. Second important property about the nuclear force is that it is an intermediate range attraction. Intermediate range attraction means it's basically, first of all, we have understood that it's it can be experienced in the limited range. Second thing, that its behavior within that range also, its behavior basically changes as per the distance. So it's an intermediate range attraction. It means when the two nucleons are at sufficient distance from one another within the nuclear volume, then only we experience this force as the attractive force. It means that when the nucleons come very close to each other, then it starts repelling also. So it means it is an intermediate range attractive force. Third important property is short range repulsion. As I told you, that when the two nucleons become very close to each other, for example, if two protons are very close, almost in the touching stage, two neutrons are almost in the touching stage, or one proton or one neutron are almost in the touching stage, then at that time basically its nature changes to repulsion. Means that they rather than attracting each other, they start repelling each other. So that is why we say that the nuclear force is a short range repulsive force. So which is basically generally termed as, which is basically reflection of hard core. Third important property is that nuclear force is spin dependent non-central forces. That in this nuclear force there are various terms, and one of those various terms is the spin dependent non-central force, like tensor force and spin orbit force. So this is basically very important part in the nuclear force, that it is not a very simple expression. Expression for nuclear force is not very simple. It's basically composed of various terms, and one of the important term in that is the tensor force and spin orbit force. And tensor force and spin orbit force arise because of the spin dependent of this nuclear force. What does that mean? It means that the strength of the nuclear force depends upon the orientation of the two nucleons, the spin orientation of the two nucleons in which the force is acting. For example, if the proton and neutron are parallel, and in the second case the proton and neutron are having their spin values anti-parallel, in the two cases the strength of the nuclear force will be different. Another important property of nuclear force is that its charge independence. It means it doesn't depend upon whether the nucleons have charge or uncharged. It means its strength is the same in between the two neutrons, in between the two protons, and in between a proton and a neutron. So more or less the strength of the nuclear force in these three cases is same. Nuclear force. We are going to study various properties of nuclear force. As we have already said that nuclear force is not a common force like gravitational and electromagnetic force. It is some special kind of force which normally we do not experience, but the subatomic particles within the nuclear domain, within the nucleus, they experience this force. And within that domain, this force basically is the strongest one. So what causes this nuclear force to be so strong and so special? We are studying the properties of that force. Now in this force, as we have said up to the last slide, we have discussed that nuclear force is a finite range force. Finite range force means this force is experienced only within the nuclear domain. Outside the nuclear domain, its value is 0 or its strength is 0. So it means the nuclear force is of finite range. How do we know about the finite range property of nuclear force? This we basically have experienced from some experiments. Now, as we all know that experimentally we can measure the binding energies of nuclei. Binding energies are nothing but the energies due to nuclear potential. Now in this case, if we compare the binding energies of deuteron, tritium, helium. Deuteron has two particles, that is one proton, one neutron. Tritium has three particles, that is two neutrons, one proton. And helium has four particles, two protons and two neutrons within the nucleus. Now if we compare their binding energies, we observe that the nuclear force is finite range force and is very strong in that range. Nuclei with A greater than 4 show saturation, which implies that the volume and binding energies are proportional to the mass number. Next important property of nuclear force is the intermediate range attraction. That is, it basically applies inside the nucleus in the intermediate range. Nuclei are bound and the average distance between nucleons in the nuclei is around 2 Fermi, which roughly corresponds to the range of attractive force. So we have seen that nuclei are bound because nuclei exist, and the average distance between the nucleons within the nuclei is around 2 Fermi. It means if one proton and one neutron is there inside the nucleus, then the average separation between the two is 2 Fermi. And this 2 Fermi is nothing but it corresponds to the range of attractive force. Nuclear force. In this slide, we continue our discussion about the properties of nuclear force. Now another important property of nuclear force is that in short range, the nuclear force becomes repulsive. That is, we have understood that within the nucleus, the nuclear force is there. It can be experienced only within the nuclear volume. Another important property is that at large distance, that is in the distance of the order of around 2 Fermi or more, the nuclear force is attractive. But when it comes to the short distance, suppose neutrons and protons within the nucleus come, or protons and one proton comes very near to another proton. Very near means around less than 1 Fermi. Then at that distance, the nuclear force becomes repulsive, and it basically termed as hardcore condition. How do we know that the nuclear force becomes repulsive at short distances? This we basically got to know from some experimental measurements where we measured the phase shift as a function of lab energy. Now in this case, basically if we plot the phase shift as a function of lab energy, we observe two curves. In the picture shown here, this picture basically is drawn for the case of deuteron, Here you can see that for the given L value we have two curves. As we know that the deuteron in its ground state has the components from L is equal to 0 wave as well as from L is equal to 2 wave, that is S wave and D wave. So if we plot the phase shift for deuteron as a function of lab energy, we analyze that they are having different nature. The nature of the phase shift, if the phase shift is positive, in one case, that is in L is equal to 2, the phase shift is positive, whereas for L is equal to 0, the phase shift is negative after certain energy. It shows that when L is equal to 0 wave crosses the 0 line, it means that after that the nuclear force become repulsive. So two different nature of phase shift indicate two different behavior of nuclear force. Now another important property of nuclear force is spin dependent non-central forces. Means nuclear force is spin dependent. Spin dependent means we know that all the subatomic particles like proton, neutron, electrons, they basically have spin, intrinsic spin. So depending upon the spin of the nucleons like protons and neutrons within the nucleus, the nature of the force or the strength of the force varies. This spin dependent component of nuclear force is called tensor force. The first evidence of tensor force component in the nuclear force came from the study of deuteron. So tensor force, we got an idea about the spin dependent nature of nuclear force from the study of deuteron. Nuclear force. In this slide also we are going to continue our discussion about the various properties of nuclear force. Presently we are discussing the non-central component in the nuclear force, which is called the tensor force. So it is observed that when the spin of the two nucleons within the nucleus are parallel, then they attract each other or repel each other depending upon what is the location of the spin. If the two particles are one over another, like as shown in on the left hand side in the right frame on the left hand side picture, then they attract each other. If they are parallel, separated by some distance horizontally, then they repel each other. So it's something like the bar magnets. When the two bar magnets are one over other, then they attract, but when the two bar magnets are put parallel to each other, separated by some distance, then they repel each other. So tensor force in deuteron is attractive in the cigar shaped configuration and repulsive in the disc shaped one. The two bar magnets provide a classic example of tensor force. So this is the summary of this slide, that depending upon the orientation of spin of the two nucleons within the nucleus, the magnitude of the value of nuclear force is different. The left hand side figure which I discussed as attractive is the cigar shaped, and the next figure is the disc shape. So when the two nucleonic spins are in the disc shape format, they repel, but when they are in the cigar shaped form, then they attract. Now if the nucleus is basically prolet, that is Q greater than 0 or positive value, and when the nucleus is oblate, Q is less than 0, then the spin is basically the perpendicular to the plane. Nuclear force, we continue our discussion about the properties of nuclear force. Now here in this picture is shown to basically show the spin dependent nature of nuclear force. Now here we can see that two protons are going towards nucleus. It means in a reaction, two protons are basically bombarded. These protons are having the spin direction perpendicular to the beam direction, when they come close to the nucleus within the nuclear domain, they start feeling the nuclear force, and as a result of nuclear force, we can see that one of the proton is scattered in the left direction, another one is basically scattered in the right direction. So it means the spin dependent nature of the nuclear force basically depends upon or includes the L dot S term. Nuclear force symmetry properties. In this particular slide, we are going to study the symmetry properties of nuclear force. As I told you that nuclear force is one of the fundamental forces, so it should satisfy certain symmetry properties. What are those symmetry properties and how we observe them? Number one, interaction must be invariant under translation. This is one of the requirements that need to be satisfied in order to observe, in order to feel this force as the fundamental force. That is, the interaction must be invariant under translation, which is basically termed as translational invariance. Second important symmetry property which this nuclear force satisfies is interaction may depend upon momentum P1 and P2 of the two particles, like two protons or two neutrons, or one proton, one neutron. So interaction may depend upon the momentum P1 and P2 of the two particles, but the only possible term showing this dependence is P is equal to 1 by 2 P1 minus P2, which is termed as the Galilean invariance. So it means this nuclear force needs to satisfy two symmetry properties. One is called the translational invariance, another one is called the Galilean invariance. Also, the interaction must remain unchanged under rotation of coordinate system. This is another invariance which basically is required for the nuclear force. It is called the rotational invariance. That is, the interaction must remain unchanged. That is, the strength of the force should not change under rotation of coordinate system. So it means if something is rotating, suppose the protons and neutrons are there, some interaction, some nuclear interaction is happening in between them, nuclear force is acting between them. So if we start rotating the system, that is, if we start rotating the nucleus, in that case their rotational coordinates will change, but due to the change in the rotational coordinates, the strength between the two should not change. So this is another important invariance condition that must be satisfied by the strong force or the nuclear force. So this is called the rotational invariance. Also, it must assume the time reversal, space reflection, which is called the parity, and isospin invariances. So there are several symmetry properties which this force has to satisfy. One is called translational invariance, another one is called the Galilean invariance, third is called the rotational invariance, fourth is called the time reversal, the property, space reflection, and isospin invariances. So these are the invariances which this nuclear force has to satisfy. Most general two-body nuclear potential under the symmetry condition is. Now so far we have seen that the nuclear force is not a common force like the one that we experienced in our life, normal life, but it is a very special kind of force which depends upon various factors, which has some very strange properties. So, and we have studied all those properties. Those properties we came to know from the experimental data. Now, if we want to write an expression for nuclear interaction or interaction potential, then we can write it as in the form that V tau sigma 1 sigma 2 tau 1 tau 2 is equal to V0 r plus V sigma r sigma 1 dot sigma 2 plus Vr tau 1 dot tau 2 plus V sigma r function of r sigma 1 dot sigma 2 tau 1 dot tau 2 plus VLS L dot S VLS tau L dot S tau 1 dot tau S plus VTR S12 VTR S12 tau 12 and so on. Now first thing that we can understand from this expression is that nuclear force composed of various terms. Now these terms have radial dependence, that is it has got the radial component that you can see that in the terms like VLSR, V0R, VLSR, VTR, VPP and so on. Also it includes the term with spin values like the terms V sigma, sigma 1 dot sigma 2, where sigma 1, sigma 2 are the spin values, intrinsic spin values for the nucleons. Sigma 1 dot sigma V sigma tau, sigma 1 dot sigma 2, like this one. Also it has the terms which depends upon tau 1 dot tau 2. Tau 1 dot tau 2 means they are the isospin values. So here you can see that the expression for nuclear interaction potential includes a number of terms. These terms basically gives you an idea about the dependence of nuclear force on various factors. Now with L dot S is equal to 1 by 2 L1 plus L2 dot sigma 1 plus sigma 2, it's a spin orbit two body operator. Q12 is equal to, this expression is equal to spin orbit quadratic operator, and S12 is equal to 3 by r square sigma 1 dot r into sigma 2 dot r minus sigma 1 dot sigma two body tensor operators. Nuclear force. So we continue our discussion about the nuclear force. In the previous slide we have seen that the nuclear interaction potential is has very many terms, and each term shows the dependence of nuclear force on various properties. Now here in this slide basically we have plotted the nuclear interaction potential as a function of distance. Now here you can clearly see that we can divide the entire nature of nuclear interaction potential into three regions: short regions, intermediate region, long region. Now in the intermediate region and long region we can see that the interaction potential is negative. Interaction potential is negative means that the force is attractive in nature. So within the nuclear domain we can see that in the intermediate range or long range the nuclear interaction is attractive, but for short distances, means in the proximity to the center of the nucleus, we find that the interaction potential is positive. Interaction potential positive means the force is negative or repulsive. So which indicates that in the short range the nuclear force is repulsive, but at the intermediate and long range the nuclear potential is attractive in nature. Three main components of nuclear force are basically central force, that is r dependence nature of the nuclear interaction; tensor force, that is spin dependent nature of nuclear interaction; and spin orbit force, that is L dot S dependent nature of nuclear force. VR terms are found semi-empirically by fitting the experimental data with some assumed forms. So students, let us summarize what we have learned in this module. There are several things which we have discussed in this module. So now we want to summarize what we have learned so far. The first thing that we have learned is that the nuclear interaction, unlike other interaction, is a complicated function of various terms. So it means, like the other interactions, what we have understood is, after going through this module, what we have understood is that nuclear force is basically not a simple force like gravitational force or electromagnetic force. So it's not a very simple force consisting of just one term or one expression, but it is basically a collection of various terms. Second important thing, at short range within the nuclear volume, the force become repulsive also. So as we have learned, when the two nucleons are almost in the touching condition, or we can say that they come very close to each other, then the force become repulsive. Another important thing that we have learned in this module is that the nuclear interaction satisfies various symmetry properties like translational, Galilean, and rotational invariance. And the fourth important property that we have learned in this module is that the parameters of the nuclear interaction are obtained semi-empirically by fitting the experimental data with some assumed forms. So it means it is basically there are various things that we have understood in this particular module.